This is ELC131, Circuit Analysis 1, and we're going to look at inductors in AC circuits. Now, up to this point, we've looked at inductors in DC circuits. However, the characteristics of inductors in AC circuits is different, and this is going to be this is the foundation of a lot of circuit operations that you'll need to understand moving to the future. Now, looking at the circuit of figure 1, we have an AC source, a sinusoidal AC source connected to an inductor. And understand that this sinusoidal AC source is going to create a voltage that goes positive and goes negative. Now, when this voltage source is positive to negative as shown, we'll have a magnetic field that is north to south. And as this voltage increases in the positive direction, this magnetic field will expand. And as this voltage source goes back towards zero, the magnetic field will collapse, as shown. Now, this voltage source will, at 180 degrees, change to a polarity of negative to positive, as shown. And this will create a magnetic field that's south to north. And as this voltage source increases in the negative direction, this magnetic field will expand and the magnetic field will collapse as the voltage source goes back to zero. Now, anytime we have relative motion between flux and a conductor will induce a voltage. And of course, this induced voltage opposes the current in the system. So this is an interesting phenomenon that alternating current makes an expanding and collapsing magnetic field that opposes the alternating current. So we look at the circuit of figure 2, which shows one cycle of a sine wave, and we'll define this as being a low frequency. Now, with this low frequency AC signal, the magnetic flux expands and collapses slowly. Therefore, the induced voltage is smaller. If you recall, one of the factors that affects the magnitude of an induced voltage is the rate of change between flux and the conductor. Now, figure 3 shows us 3 cycles of a sinusoidal waveform, and we'll define this as being a higher frequency. And of course, with this AC signal, the magnetic flux moves in and out. It expands and collapses much faster. Therefore, the induced voltage will be larger. And since the induced voltage opposes the current, the opposition to current will be greater. So we've got a new quantity to remember, and that is reactance, symbolized with the letter X, measured in ohms. The unit symbol is the Greek letter omega. Reactance is the frequency-dependent opposition to a sinusoidal alternating current. Inductive reactance, symbolized with X sub L, is the reactance of an inductor. Mathematically, X sub L equals 2 pi FL. So, looking at a problem, we're asked to calculate the reactance of a 100 millihenry inductor at a frequency of 1 kHz. So X sub L equals 2 pi times 1 kHz times 100 millihenries, which gives us 628 ohms. Now, when discussing inductors, remember that an inductor has two inherent quantities, the value of inductance and some value of wire resistance. Again, an inductor is made of a great length of wire, or a length of wire wrapped around some core, and wire has resistance. So when we discuss inductors, we have to take into account both the opposition to current caused by the expanding and collapsing magnetic fields, X sub L, and the opposition to current caused by the wire resistance. And one metric we use to quantify inductors is the quality factor Q, which mathematically is X sub L over RW. So again, we look at an example problem, and we're asked to determine the Q of a 100 millihenry inductor at a frequency of 1 kHz with a wire resistance of 100 ohms. And of course, the Q factor is 628 ohms. This is X sub L from the previous problem, divided by the wire resistance 100 ohms, which gives us a Q factor of 6.28. Now, it's important to note that Q has no units, because mathematically we have ohms divided by ohms, so the units cancel. And again, this is just a number. There are no units to the Q factor. Now, we look at the equation that we were given we looked at in the previous video, which says the induced voltage in an inductor equals the value of inductance times di dt. And again, these symbols, D, the symbol D is from calculus, which is used to identify the change in a quantity. So di dt is the rate of change of current. Now we look at the sine wave in figure 5, and at 0 degrees, this point right here, the slope of this sine wave is large in a positive direction. So at 0 degrees, di dt will be a large positive value. At 90 degrees, the rate of change of current, or the slope of this sine wave, is 0. Because as time moves forward, the current doesn't change at this point right here. At 180 degrees, the slope of this sine function is large in the negative direction. At 270 degrees, the slope of this function is again 0. At this point right here, current isn't changing. And of course, at 360 degrees, we're back at our starting point of 0. So at 0 degrees, di dt has a large positive value. At 90 degrees, di dt is 0. At 180 degrees, di dt is a large negative value. And at 270 degrees, di dt is 0. So again, from the previous slide, we saw that at 0 degrees, di dt is 0. Therefore, at 0 degrees, VL is a large number, a large positive value. At 90 degrees, since di dt is 0, the induced voltage will be 0. At 180 degrees, di dt is a large negative value, so VL is a large negative value. And of course at 270 degrees, since di dt is 0, VL will be 0. And at 360 degrees, we're back at the starting point, and VL has a large positive value. So looking at the sine waves in figure 6, note that voltage and current do not happen at the same time in an inductor. That the voltage leads the current by 90 degrees. Now, in the old days of electricity, source voltage was symbolized with the letter E. So students in electricity and electronics would remember that voltage happens before current in an inductor by remembering this ELI. Voltage leads current in an inductor. So if you remember ELI, it'll help you remember the relationship between voltage and current in an inductor. Now, trying to represent or illustrate this phase difference between voltage and current in an inductor is difficult by sketching the sine waves that we saw in figure 6. So what we do is we illustrate this phase difference using a vector diagram as shown in figure 7. Now on this vector diagram we place or we represent current and voltage as what are called phasor quantities. Now if we look back at figure 6, we see that current was the sine wave that started at 0 amps at 0 degrees. So on this vector diagram, we're going to use current as the reference. In other words, it is at the positive or placed on the positive x-axis, or this point on our vector diagram is our reference point, or 0 degrees on this vector diagram. And since voltage happens 90 degrees ahead of current, we put voltage, the inductor voltage, at the positive, on the positive y-axis, so that it is 90 degrees ahead of the current. And we're going to use these vector diagrams to illustrate the relationship between voltages and currents in our circuits for the remainder of the semester. So this is a concept that you need to be familiar with. So again, with inductors in AC circuits, we have an expanding and contracting magnetic field, and this expanding and contracting magnetic field induces a voltage that opposes the current that makes the magnetic field expand and contract. The higher the frequency of this AC current, the greater the induced voltage. And we quantify this opposition to AC current with reactance, symbolized with the letter X, and the reactance of an inductor, X sub L, is 2 pi FL. And again, inductors have two oppositions to current, the value of inductive reactance and the wire resistance. So we use the quality factor Q to quantify this relationship between inductive reactance and wire resistance. And lastly, we looked at the phase difference between voltage and current in an inductor, and we see that voltage leads current by 90 degrees in an inductor.